Good afternoon, everyone. Today we're going to be looking at an example of geometric sequences in action where we have the situation where Caden's salary increases by 2.5% per year. He's been working with Google for 8 years and he currently makes $80,000. So what was his starting salary 8 years ago and how much is he going to make in 5 years' time? So first off, let's write a general formula for his salary based on the number of years since he's been at the company. So we'll say that we can say U0, U0, let's say his initial salary is going to be what we're looking for. So that'll be his initial salary. We know his salary after 8 years, so U8 is $80,000. The common ratio is going to be 1.025 because if his salary is increasing by 2.5%, then his salary is 102.5% of the previous year's salary, right? If we're increasing by 2%, by 2.5%, then we're increasing 100% of his previous salary by adding 2.5% to it, which of course brings it to 102.5% of his previous salary. And 102.5% as a decimal, which we need for our common ratio, is of course 1.025, okay? And that is how much we're multiplying his salary every year so that it increases by 2.5% per year, okay? So with this information in mind, we can write our general formula for his salary after n number of years at the company as UN is equal to U0 times 1.025, the common ratio, i.e. increasing by 200% a year. Again, every year he's making 100% of his current salary, obviously, and so increasing it by 2.5% brings it to 102.5%, which as a decimal is 1.025, and then to the power of n, because I don't have to write n minus 1 in the exponent because we made our initial salary U0 or U0, as some textbooks call it, not U1. And so we will only be multiplying that initial amount n number of times to get his salary in the nth year, okay? There's always this relation between the starting point and the exponent, depending on the number of times we have to multiply to get to the nth term, okay? So just keeping that in mind, now we have our general formula. So since we know that U8 is $80,000, we can find his initial starting salary because that means looking for U0, right? Now, U8, of course, would be equal to U0 times 1.025 to the power of, well, the nth term in the sequence, the nth year's salary requires us to have 1.025 to the power of n, and so the 8th year would require us to have 1.025 to the power of 8, which means that now we can plug in our value. U8 is 80,000, and so maybe let's do that over here. So we have 80,000 is equal to U0, U0, times 1.025 to the power of 8, and now we're really down to just a bit of algebra. And so let's do that together. First, we can calculate 1.025 to the power of 8, or if you'd rather do the algebra before computing this value, we can do that as well. We can divide both sides by 1.025 to the power of 8, divide by 1.025 to the power of 8. That way they cancel out here, and right away we can compute U0. If you have a nice calculator, that will do it all in one step. 80,000 divided by 1.025 to the power of 8, and that brings us to $65,660 rounded to the nearest dollar. And so since that is U0, U0, that is his initial salary, his starting salary, okay? So that is part A. Now, part B, what will his salary be in 5 years? There's two kind of natural ways we can do this based on the information that we're given. We can either look at U0 and then increase that salary based on his initial salary. He's already been there for 8 years, right? So from U8, if we want to go another 5 years into the future, that would be a total of 8 plus 5, 13 years at the company. And so we could write this as U13 and have U0 times 1.02 to the power of 13. Or we can use the general knowledge we have about geometric sequences. We could write either U13 is equal to U0 times 1.025 to the power of 13. This is maybe the most straightforward way to go about it. But we also know that there's no specific reason why we need U0 to be in this position. It's convenient to have a starting point, but we can also have his 8th year salary as our starting point if we wish to do so. We can also write U13 being equal to U8, which we happen to know, times how many times is his salary going to increase by 2.5% between his 8th year and his 13th year? Well, that'll be 5 years worth of salary increases, right? And so we're going to multiply his 8th year salary by 1.025 5 more times, successively every year. And so we could raise our common ratio to the power of 5. And this should give us exactly the same value for U13. We can go ahead and check that. So since we found U0 in part A, we could write this as 65,660 times 1.025 to the power of 13. And if we want to check that both ways do indeed give it the same answer, we know that U8 from the information given in the question is 80,000 times 1.025 to the power of 5. And then if we want to compute both of those to verify our conjecture, presumption, assumption, whatever you want to call it. Let's go ahead and do that. So we have 1.025 to the power of 13 times 65,600 gives us $90,513. $90,513. And let's see if that's equal or at least comparable based off the tiny bit of rounding that we didn't find in U0. 80,000 times 1.025 to the power of 5 this time, and that gives us exactly the same dollar value when we round to the nearest dollar. And so there we go. Two different ways of finding the same kind of information, which is often the case with these kinds of problems. There's often different ways to think about it. As long as your algebra, as long as your solution is well written out and logically sound, we shouldn't have any problems. So I hope this helps. I hope this starts making connections between geometric sequences and later on what you'll probably see in financial mathematics. Hope this helps. Thanks for watching.